Hey there, and welcome to our ECPE/CIVL 293A projectile project, where Eiskamp, Isaac, and me will show you why we made a foam airplane do this.
It is a well-known fact that forest fires cause a great amount of damage to the environment and people's property. Extinguishing these fires requires a significant number of people and courage on the part of those people. To help with this and reduce the danger, people are using unmanned aerial vehicles to automate the process of putting out fires. This requires that the unmanned aerial vehicle be able to determine where the fire is, when to release the payload, and how to land safely after the payload has been released. For this project, our goal is to monitor motion of a projectile at launch and during flight, and then to determine when to release a payload based on a sensed and computed data and ensure a safe landing of our projectile. Our objectives that we wish to determine include the design of a system which uses sensors to monitor and compute projectile flight. We are also required to build a system to launch that projectile. We are going to compare theoretical flight trajectory to experimentally measured flight trajectory, and build a detection system to locate the event of interest, which is in this case whatever our heat source is representing the fire. Once that has all been done, the hope is that the built system will release the payload, hopefully hitting the target. For this project, groups are required to construct a launch structure and a projectile with a water balloon release system. Each group is provided a microcontroller to allow for data collection. In this case, the data reflects the motion of the projectile system and the location of the fire. For materials for the project, groups are required to purchase or salvage the remainder of the materials for the design. What is most important is that the system works and survives once impacting the floor. Once a team has designed, planned, and implemented their system, testing of the system will occur, in which teams will compete for the most accurate height indicator and closest drop to the fire. The group is required to perform all actions in real time. For the projectile, we had some initial considerations. At first, we thought a hang glider would be a good choice, realizing that we would have to put the hang glider at a high point and project it outwards, hopefully having the hang glider go over the heat target, dropping the water balloon. Another consideration was a blimp. We could have the blimp take off, sense the target, and then make its way over the target where it would eventually drop the balloon onto the target. Third consideration was a rocket, in which basically we would project the rocket quickly and drop the balloon way before reaching the target, ensuring that the rocket would pass over the target and that the balloon would fall and hit the target.
But none of them really worked. We decided that the hang glider was too complicated to make. We had just too much to it. It was too difficult. The blimp, it was too high cost. It was too dangerous if we wanted to use some type of fire, and it was hard to control and program the detection system on it. Then the rocket, we decided it was too fast and too dangerous, and when we were testing it out, we figured it was too unstable when we were launching it.
Instead, our final design incorporated the use of a foam glider that simulated a jet takeoff from an aircraft carrier. So as you see here, this is our initial plane. Obviously it did not withstand all of the test flights that we did, so we actually had to go and get another one. This here is our final model. Obviously just a regular styrofoam plane without any of the, the weights or anything on it. It's a great glider, glides about 150 feet, tested it, everything's great. As you can see, there's all our weights. Anything that weighs is not congregated into one area, it's all distributed. We have our battery pack, we have our servo, a sensor on the front. Underneath, we had to cut a slit in the plane for a water balloon. Holds up to half a cup. Obviously we went with a quarter of a cup of water. Included this just system. It's a piece of cardboard. We thought it was lightweight enough. It wouldn't obviously damage the floor of the gym. Easily fixable, easily able to release the water balloon. Also on the bottom here are these skewers. The skewers actually create a little bit more lift, doesn't allow the plane to drag so much on the surface of our apparatus. This allows the servo to not drag as much either. That was something we were concerned about, is this actually catching on the wood, this servo here catching on the wood and falling off. So that those sticks allow for that. As you notice here, we have these guides. These are just pieces of plastic, very moldable and everything like that, easily fixable. We've duct taped them in place to ensure that the plane can follow the tracks of the apparatus, making sure that the plane goes straight. As you can see, there is a ton of duct tape covering our plane. Initially, when we did our first flight with the apparatus pulling it back using the bow, what happened is all the wings actually fell off. They actually just came off. The force was too great. The drag acting on the tail end actually caused it to rip off, and thus we went with duct taping. So we had to duct tape everything, make sure everything stayed stable, stayed together, and allow for a good flight.
So initially, for our launching mechanism, we wanted to do some type of propulsion, like a small CO2 cartridge. Then we decided we wanted to do something like a helium balloon, use some kind of spring system, maybe make a trebuchet. Then we decided that we wanted to create a system where we could just display something that creates some type of force and could be repeated over and over again. Therefore, we went with a crossbow system with some type of PVC pipe and wire.
Initial crossbow was made out of a 3/4 inch PVC pipe. When we were testing it out, we realized when we pulled too far back that it would just permanently deform. So to stop this, we went with a larger 1-inch PVC pipe, and we used a 1/16 inch wire. The original base was able to be angled because we thought that there wasn't going to be enough lift. The materials we used a 5-foot 1-inch PVC, then we used a 4x8 sheet of plywood, which we cut down to size. We used a bunch of duct tape, the 6-foot 1/16 inch wire for the bow, and some fasteners on the side so the string won't slip, and some various scrap wood that we found, and screws varying from 1.5 to 2.5 inches.
This is our launching system. It is about 4 feet tall. We have the holder over here carved out so that we can put in the bow nice and snug. We had this strip down the middle cut out, kind of thin piece, where we put in the little plastic holders on the plane to keep it straight when it shoots out. And we measured in increments how far back we have to pull to get a certain amount of force, like 20 pounds, 25, 35, and we decided to shoot it at around 45 pounds. So we have a constant thing right here. And then in the back, we have these to just stabilize it and keep it from moving. Pretty simple.
So, in terms of using the bow, what is required is once the bow has been placed in the holder, you can actually go ahead and set it up. The way this works is you just grab the handles, pull back. As you can see, the bow deflects. The screwdriver, which acts as our pin, follows along the path until we get to the 45-pound marker and is held in place. In terms of release, all that's required is we remove this pin, it releases the bow, and releases the airplane.
I will now go over the electronic devices that are on our projectile. Up here we have the IR sensor connected to the Arduino up here, also the servo that controls the door. We also have an ECPE right here in the back that wirelessly transmit the temperature readings just for the sake of monitoring on a separate device. When I plug this in, it'll go through its initial setup. It automatically opens and closes that. This yellow LED tells us that it is in standby, it is ready to actually start collecting data and start our flight. So when we push this white button here, green LED will turn on, telling us it's collecting accelerometer data, logging it to the SD card, and whenever we see something warm in front, the servo will open, deploying the door and releasing our water balloon. When it was removed, it goes back to the reset position, so that when we land, the door isn't open, there's nothing that can catch on anything and potentially damage the plane. We can then stop this, turning off the green LED, turning on the yellow LED, and essentially we can keep running further tests. Push the button, start again, see something hot, door opens, yellow LED turns on, remove it, closes, and that is how we are collecting the data on our device and how it operates.
So here we'll describe our free body diagram for our dynamic system. As we see, we have a plane in flight. So first and foremost, we're going to use block diagrams. Block will represent the mass of our plane. Forces that we're looking at considering are, one, our force of uplift, force of lift. We have a force of drag due to air resistance. We have force of weight. So we have a weight, which is just our mass times our gravity. And we have our initial force that is projected by our bow system. We'll call this our force of bow. So, using this system, we were able to develop a set of equations. On the top here, you'll notice our force of drag is a product of our coefficient of drag, the density of the air, our initial velocity in the x direction, and the area of the cross section of the plane wing, and our force of uplift, which is a product of our coefficient of the wings, our density of air, the velocity in the x direction again, and the area of the wings. Following this, we had to determine steps for when the velocity increases. So our velocity at the second step is the velocity initial minus our force of drag times time over the mass of the plane. This generates our next velocity term per time step. For our velocity in the y direction, we had to incorporate the use of our force of lift times time over the mass of the plane, which gives us our initial upward velocity, and then we have to subtract out per time the gravity that's taking effect. As you see, these all loop into one each other, and so as the force of drag and the force of lift decrease with velocity as it decreases, so do the time step velocities. Finally, we're able to model our system using our position vector or position equations. For our x direction, we included our velocity at that current time step times time, and we have to subtract out the deceleration due to the force of drag. And for our y position, we had to take our velocity in the y at a certain time step and subtract out the force of gravity acting on that.
So to model our bow, we went with a simple cantilever beam, and to find out the deflection needed for a certain amount of force, and all we had to do is just use this equation, which is easy to find. We find the modulus elasticity by finding the force required to pull it a certain length, and we know the modulus, we know the moment of inertia for these. All we have to do is through the equations find out what is the required force needed, and then find out the distance required to pull back the bow. The bow is simple enough on our system. It gets pulled back, and there's pulling P on each side, basically two cantilever beams, which goes directly into our tension, which is our required force. And through this equation, we can find out how far we need to pull it back to get our required tension and force.
Alright, so now I will be going over the data that we collected during our flights on demo day. This is one of the flights that we had. This is the first flight. Looking at the data, this data that I graphed here, it is the accelerometer data collected from the IMU in the ETS and Y, or ETS and Z axes. You can see on both there's a very large jump in the accelerometer data followed by some oscillations. The first jump is the force at launch. So we see a large spike in the X, a large spike in the Z here. And then the last little jump is actually where it landed and hit the ground. It's pretty noisy. Even from this, I used just a simple filter, took a moving average of 10 of the values to try and get this data to look a little bit more smooth. But these IMUs aren't that great, so there's still a lot of noise in here. And to further back up the claim that this is the actual flight data, even though this is taken over a long period of time, I graphed out the actual time at each iteration. So have over 2,000 data samples. Time goes from 0 to about 75 seconds. You'll notice this little jump in the time here. Everything else is pretty constant, but right here is where there's actually about a half a second delay. And this half a second delay is something that I programmed into the microcontroller to allow the motor to open the hatch and deploy our water balloon, making sure it has plenty of time before closing. Just under 29 seconds is where this occurred. Adding about 2 seconds around that should give us the time for our data. And I took the accelerometer data just for this time, so I have going from about 27 seconds to 31 seconds. And I went ahead and actually graphed this data. Here you can see the X versus Y, or X versus Z axes. You can see that our data shows our projectile going forward, and then for some reason it shows it going back past where we launched it, still rising. Don't know why exactly the data shows this, but you could see in the other graph that it was pretty noisy. However, using that time data, I can actually say for a fact that this is the data of our flight. This just goes to show that these IMUs we were using weren't exactly the most accurate. Obviously, I could have done a better job of actually collecting this data. I just had it running, saving to an SD card. Actually going back and finding it was a bit of a challenge, but luckily with that time delay, I was able to find it. If I had more time, I could probably go through, do some further analysis, maybe even collect more data. We don't exactly have the time to do that, so this is what I ended up with. So in summary, we were able to find the data that was from the flight, but it doesn't exactly show our exact trajectory.
So in conclusion, we found that our glider worked very well for modeling a UAV. It was lightweight, we were able to modify it quite easily, it was cheap, and a lot of the parts were replaceable. Although the heat sensor did not perform as well as we hoped, it did not sense the heat pad fast enough. It did sense it while it was in flight, and it did drop the water balloon, but it did it right after it flew over the target. It did successfully launch the projectile directly at the target, and we were able to repeat it without failure.
So as for our comparison between our theoretical and experimental data, as you can see, we came up with this graph of our theoretical trajectory. This shows it going about 11 meters in the X direction and up about 1 meter. If you remember our actual flight data, or our actual flight test, we did go about a meter or so up in the air before landing about 40 feet after we launched. Now when comparing this to the data we collected from the accelerometers, obviously it didn't quite match up the way we had hoped it would. However, this does prove that our theoretical calculations matched what actually happened in reality.
This is our budget. We were able to stay under $75 with our $71.74. With our most expensive items were the sensor at about $21 and the plywood at about $17. And we were able to salvage most of our materials. This is our schedule of our hours.
As you can see, we all got about the same amount of hours, of above 35 hours each, even with the handicap of Thanksgiving break.
This concludes our report. We hope you enjoyed the video, and please feel free to watch our final launch of the Raptor 1856.